Forests are of great importance for society. In order to provide their valuable services in the long term and sustainably, they must be managed with regard to this goal. In steep terrain, but also increasingly in flat areas with sensitive soils, cable yarders are often used for timber extraction. Cable yarding operations are demanding. Even the design of a single cable road is complex. The skyline tensile forces must be within acceptable limits. A sufficient distance from the skyline to the ground is necessary, and suitable support and anchor trees must be identified. Therefore, the research project New Basics for Cable Road Design aimed at developing improved foundations to support cable road design. To this end, the Seilaplan design tool, designed at ETH Zurich and WSL, was further developed at WSL, and the implemented calculation method was verified in a field trial. To use the Seilaplan plugin, the freely available software QGIS and an elevation model is required. The elevation model can be downloaded with the plugin Swiss Geo Downloader. The course of the planned cable road is drawn on the map and the technical data is entered. The proposed cable road layout can be adjusted manually and saved as a diagram, report, or GIS layer. Leo Bont compared two methods for calculating a cable road as part of the research project. The Pestal method, which is widely used in forest practice, and the rather unknown Zweifel method.
The Pestal
method assumes that the skyline is weight tensioned, similar to the passenger cableway. When a carriage moves along the span, the horizontal component of the cable tensile force remains constant. For forester cable yarders, however, the skyline is fixed at both ends. As a result, the skyline tensile forces are changing when a load is moving and reach their maximum in the middle of the span. This can be described mathematically with nonlinear systems of equations. This is also referred to as the catenary.
For the comparison of the methods, field measurements were carried out on 4 different cable roads with different load configurations. For each load, a height measurement device was used to determine the distance between the skyline and the ground in the middle of the span. Based on these data, the sag was calculated. In addition, the skyline tensile force was measured with a load cell at the anchor.
The evaluations of our field measurements have shown that the calculated sags according to Zweifel are more accurate than those according to Pestal. The differences between Zweifel and Pestal are particularly obvious for long spans or for heavy loads. Furthermore, the occurring skyline tensile forces can be predicted precisely with the Zweifel method.
Seilaplan, with the implemented calculation method according to Zweifel, has already been tested in forestry practice. One of these users is Niels Schönenberger, who has already set up several cable roads with Seilaplan and thereby gained first experience.
Thanks to Seilaplan, finally, we have a software with which we can design cable roads quickly, efficiently, and in just a few steps. This considerably facilitates our work in the development of detailed forest access concepts and for the realization of cable yarding operations. With the generated report, our employees can efficiently install the cable roads in the terrain. The calculated data match when operating the cable yarder, and there are no deviations or changes during setup and yarding operation.